Okay, you hopefully saw the message that I sent through the Google that I discovered after class. I remade the measurements, but only using one oscilloscope instead of 4. And the values were very different. The oscilloscope leads were, because you have impedance in your voltmeter, was messing up the measurements. So the actual voltage you should have had was somewhere around 5.6 volts based on the measurements that I gave you. And that was because of interference, absorption, energy being absorbed in the meters. I should have taken more time and just gone and changed the leads. I just thought it would be cool to be able to make measurements all at once. We learned. Of course, you probably didn't have a lot of faith when you saw that it didn't come out to have a total voltage equal to the total voltage. I'm sorry about that. If you choose to redo it with the correct numbers that I put in that message, you'll see that you get correct values. Okay, today, chapter 24. What is chapter 24? Chapter 24 is a connecting chapter where we tie up the pieces of electricity and magnetism and start into optics. So, before we do any clicker questions, I do have to save the last class and close it, because I think I don't have a clear question coming up right now, so I'm actually reasonably safe. This graphic here shows you a lot of things about electromagnetic waves. The first thing you see is that it shows equations for each of the electric field and the magnetic field. An electromagnetic wave is a wave that has both an electric field oscillating and a magnetic field oscillating. Something to notice about these two equations is that part there is the same for both of them. The electric field and the magnetic field are oscillating in unison. So when the electric field is at its peak, the magnetic field is at its peak. When the electric field is at its minimum, the magnetic field is at its minimum, and so on. Second thing to note is the directions. Notice in this picture, the electric field is in the y direction, the magnetic field is in the z direction, and the velocity is in the x direction. For electromagnetic wave, the electric field and the magnetic field and the velocity are all mutually perpendicular. Mutually perpendicular means each one is perpendicular to the other two. If we come down and look at this equation right here, it gives us the basis for a right-hand rule. And that right-hand rule is, if you can't divide vectors. There is no mechanism for dividing vectors. But if I multiply across, that equation becomes E max equals B max C. And that leads to the correct equation that at any moment in time, the electric field is equal to the magnetic field crossed with the velocity. So if you look at the directions here, see the blue line for magnetic field, B cross V. The C is the symbol we use for the speed of light. And so the velocity of the wave has a magnitude of c and has the direction shown by the green arrow. So you take your right hand and you go B cross V, and then your thumb points in the direction of the electric field. And so in this graphic that shows the electric field traveling through space, the magnetic field traveling through space, you see that the magnetic field and the electric field initially are matching the direction shown in that little diagram. And then the magnetic field reverses because it got weaker and goes the other direction. The electric field likewise reverses and goes the other direction. So you still have that right-hand rule maintained. No matter where you are in the wave, you have to have the electric field crossed with the magnetic field crossed with the velocity is equal to the electric field. So they're mutually perpendicular. You don't have to worry about something in between. It's always right angles with the electromagnetic waves. That's just our introduction. That had no theory behind it. That was just facts. So let's look at where this comes from. So to get where it comes from, we have to go to James Clerk Maxwell. His father was born Clerk. That was the family last name. but they had a friendship with the Maxwell family, and the Maxwell family let them inherit some stuff, including the name Maxwell. And so James Clerk Maxwell had an additional last name of Maxwell from that inheritance. So I always point this out because, everybody talks about Maxwell, but, his last name, Clerk, is the more accurate, and Clerk Maxwell is the best way to refer to him. So what did Maxwell do? See, I just said Maxwell. Between 1855 and 1861, he sat down to try to unify all of the known information about electricity and magnetism. And in 1861, he wrote a paper where he was able to bring it down so you only had 20 differential equations with 20 unknowns to solve. And as I said up there, yuck, right? 20 differential equations with 20 variables to solve. I don't want to do it. Right? Those guys had to be really, really devoted to try to solve those kinds of problems. But then he continued to work, and 12 years later, he published his final simplification that brought it down to just 4 differential equations with, 2 vector variables and then 2 others, a few others. A very, very simplified view. And so now physicists look at electricity and magnetism and say, isn't that amazing that all of this wealth of complicated material, and you can't say at this point that everything we've learned was simple, right? Pretty complicated stuff, can be broken down to just 4 laws. You can explain it all with just 4 laws. And so his theory, those 4 laws, predicted that electricity and magnetism could support waves. Now, if we think about what we know about waves, waves are a way of transporting energy. And with a wave, you have energy change from one type to another. Well, in this case, you can have energy in electric and magnetic fields that's being swapped. And that's what's transporting the energy. And based on his 4 equations, and we'll do this in class next Tuesday, so everybody say yay in calculus class, he was able to actually calculate the speed that the wave should be. And I have that calculation coming up in a few pages, but not right here. And he found that speed was the same as the speed of light. And then he made what I consider a horrible, horrible logic decision that turned out to be right. He said, well, light has this speed, electromagnetic waves have this speed, everything must be the same thing. That would be kind of like saying, if I am running and the car is driving beside me at the same speed, ergo I must be a car. Right? That's pretty flawed logic. And today we understand that gravity also has that same speed. Nobody says gravity is the same thing as light. But it turned out he was right. So it goes down as a stroke of genius because he was right, even though his logic was pretty flawed. So what are the 4 final equations? The first one, Gauss's law. We've used Gauss's law. We saw that Gauss's law said that the electric flux going through a surface is equal to the charge enclosed divided by just a constant, the permittivity of free space. So that one says that you can have electric fields created by charge. Then we have Gauss's law for magnetism. And I said it exists, but we never use it in this level of class because no matter what your shape, how much magnetic charge do you have enclosed? 0, because magnets don't come in monopoles. They only come in dipoles. You guys may or may not have heard of physicists I can't remember his first name, but the last name is Guth, who is famous for coming up with the inflationary model. The inflationary model says that in the early stages of the Big Bang, you had expansion, and then all of a sudden there was a new force available, and you had a big expansion. He got into this because he was studying magnetic monopoles. And he theorized that the only way, if you read his book, he's actually got a sense of humor. The only way that we can make these magnetic monopoles would be to make a particle accelerator that extends for many, many light years and then accelerate particles, but the government wouldn't pay for that because, of course, it's completely impractical, not possible. And so when he did his work, he theorized that the only time in the entire universe that there was enough energy to create a magnetic monopole would be during the Big Bang. And it could have made as many as 4 or 7 magnetic monopoles. So theoretically, magnetic monopole could exist, and there could be 7 of them distributed throughout the entire universe. Hence, what are the chances of us ever finding one, even if one exists? Vanishingly small. As far as we know, they don't exist, but they're theoretically possible. Okay, so we have Gauss's law that says that a magnetic charge would create a magnetic field if we could get a magnetic charge by itself. Then we have the last two, Faraday's law of induction. The law that says a changing magnetic field creates an electric field. Now, we saw it a little bit different. We saw a changing magnetic flux created a voltage. That's the way we saw it. But as we'll see on another slide or two, that is the same as saying that a changing magnetic field creates an electric field. And then there's the Ampere-Maxwell law. Oh, we've got the word Maxwell because he contributed to one part of one of the 4 Maxwell equations. They're called the Maxwell equations because he's the one who unified them. And at first it seems trivial, but then when you think back, there were so many equations and he was able to sift through them and come down to these are the fundamental ones. But he had to change Ampere's law. So what do you know for Ampere's law? I'll write down the equation that you know for Ampere's law. The circulation, the integral of B dot dl over a closed surface, or for non-calculus, that'd be sum of B dot L over a closed surface, or closed loop, is equal to mu naught times the current enclosed. That is, a current creates a magnetic field. That's what you know for Ampere's law. But Maxwell realized that there is a flaw in Ampere's law. And that flaw is illustrated with capacitors. If I have a capacitor, and I look just here at the current, at the current coming into the capacitor, and I apply Ampere's law, everything's hunky-dory. It works perfectly. But if I move to between the plates, how much current is passing right here? None, because a capacitor, no conductance, there should be no current there. But is there no magnetic field there? Let's try this another way. You could take this loop, and it says the current going through it, right? Well, what defines what's going through? You just have to close the surface. So most of us would just close the surface right here and say, yep, that wire went through the surface. But we could just as well, just as accurately, make our surface so it goes like this. Just think of it like a balloon. We blow out the balloon. So instead of being cut by the wire, it's going between the plates. Now there's legally no current going through my loop. Did that change the magnetic field because I changed where I'm counting? No, it couldn't. And so there had to be a flaw in Ampere's law. He found a flaw. So once he found the flaw, well, of course, you have to fix it. And so he said, well, look, we know that for a capacitor, we have a relationship that says the charge separation of the capacitor is equal to capacitance times voltage. And so since current is the change in charge divided by change in time, remember these D's just mean change. It's the same as the delta for people who aren't in calculus. It's just a smaller delta is all it means. So I could substitute, instead of change in charge divided by change in time, I could say change in capacitance times voltage. And then put in the equation for the physical capacitance. So this is physical capacitance. If it's an air-filled capacitor, that's the permitted free space, epsilon sub 0, multiplied by the area of the plate divided by the separation of the plate. So that's the capacitance. And then the electric field, if we're in a parallel plate capacitor where the electric field is uniform, pointing from one side to the other, then the voltage difference is EL. Remember we had, like on the test you had this, the change in voltage is equal to E dot delta X. So if E is uniform and delta X is the same direction as E, then that just comes down to the voltage difference is EL. Well, we can cancel the L's. Since epsilon 0 is a constant, the epsilon 0 comes outside. And what was EA? Not in the game. EA Sports is in the game. EA is the electric flux. And so he said, there is an equivalent current going between the plates of the capacitor due to the building of the electric field. And that equivalent current is called the displacement current. And just like electromotive force, the name is anachronistic. There used to be a displacement theory that has been disregarded, discredited. I don't know what it is, but we still use the term displacement current. And so this here is the displacement current. That's the effective current when you have a changing electric field. And so he said, if we look at Ampere's law, we have to replace the current in Ampere's law with this plus our displacement current. And so this, okay, I switched or I mixed calculus and non-calculus. There, now it's a calculus equation on top, on bottom. So this is the Ampere-Maxwell law, where we have included the addition that Maxwell added that says that changing electric flux will induce a magnetic field. Electric flux, result of electric field change. So those are the four equations. I will answer your question as soon as I get to this slide. What's your question?
Well, I was going to say, was it mu or sigma on?
Oh, did I use, well, this is epsilon 0.
That's what I meant. Epsilon 0.
And so you're right. I wrote that wrong. Thank you. Because it is really embarrassing to have things wrong. Even though I put this on YouTube, and there are people outside this class who do look at these occasionally on YouTube, they can see my mistakes. It was funny. One person actually made a comment where they were arguing with me, saying I taught my students wrong, but I didn't, and I think they realized it and deleted the comment before I could reply. So here are Maxwell's equations, summarized. These don't look like the equations you learned, do they? These are most clearly calculus equations. We can write them in two forms, the differential form. So people in the Physics 252, you use that top form and the differential form on your homework, the calculus homework. Or there's an integral form. The integral forms are more similar to what we've done. Right, this one here is what we learned for Gauss's law. The electric flux through a closed surface, dV there is written because you're doing a volume surface. The circle is because it's closed. The dA is because you're doing the surface of it. Right? There's reasons for everything here. So this side here is the electric flux is equal to the charge enclosed over epsilon 0. It's what we learned. But it's written in a calculus form. Over here, it's written in a differential form rather than integral. The magnetism one, the magnetic flux is equal to 0 on a closed surface because you have no charge enclosed. And then we have these. This here, the right side is basically what you learned for Faraday's law of induction. We had the minus sign, and then we had N because we were allowing for multiple terms. This doesn't have the N. And then we have the change in magnetic flux over change in time. The left side, the integral of E dot dl, I actually just did that on the last page. Integral of E dot dl, by definition, is the voltage change. And so we learned voltage where it has the integral of E dot dl. This one here, which is the one we're going to use in class next Tuesday, Del cross E, happy, happy, joy, joy, right? Del is a three-dimensional derivative and then a cross product of the electric field. Don't worry, we will use some identities to make it easy, those of you who are looking forward to Tuesday class. And then finally, we have the Ampere's law as modified by Maxwell. So using these equations, he combined them and said it produces light. So we physicists think we are some of the funniest people on earth. It's probably true. And physicists like to wear shirts like this. I have one somewhere that says, God said, and then it puts the four Maxwell's equations. And then there was light. Because the Maxwell's equations give us what we need to support light in physics. So we think we're really hilarious by wearing these shirts. Just wanted you to know that they exist. Let's have our first clicker question. How many equations are necessary to describe all of electromagnetism? I shouldn't be laughing. Somebody's just moving their answer around to be funny. Okay, all of us have answered. And all 20 said 4. G was a meaningful answer because in Maxwell's first bringing it all together, he got it down to 20. But then 4 was what he got it down to a dozen years later. And that's where we stand today. So, another clicker question. How many of these equations did James Clerk Maxwell create on his own? Okay. We have one person that said all 4, one that said all but 1, 4 that said 1, 12 that said part of 1, and 2 that said none. So let us see what Isaac has to say. What do you think, Isaac?
I put 1, but looking back at it, I realized that it's E. So I put 1 thinking that he took Ampere's law and he kind of made it his own. He made some changes and stuff, but at the same time, it is he made part of 1. Ampere's law was still there.
Okay, I'll take that. That's a good description. He showed that he knew what was going on here. That he took Ampere's law, named it by name, and he modified it because he found a flaw in it. And of course, when we look at this, it seems to trivialize the work of James Clerk Maxwell. You know, he modified 1 equation, and then we have 4 equations that we call them his and woohoo. But then when you realize that he sifted through a whole bunch of equations and was able to all melt it all down, you know, do we see Coulomb's law? No, because Coulomb's law and Gauss's law are redundant, right? So he was able to filter it out and get us down to what we need, and that really is pretty good work, worthy of esteem. Okay, so what do we have from Maxwell's equations that would support electromagnetic waves? Basically, if you have an accelerating charge, it's going to produce an electromagnetic wave. If you have a charge that's moving, it will create an electric field and a magnetic field, but they won't be oscillating. You have to have it accelerating to get the oscillation. So if we have accelerating charge, we can set up an electric and magnetic field and have those then be self-perpetuating. Right? To be a wave, it has to be self-perpetuating. It can't, just die. So here's a basic how we get the electric field. Let's see, do I have those right? V cross B, nope. There's a sign error here. Remember from the opening slide when I did electric field is equal to B cross V, V cross, or B cross V. B and V sound so similar. So I fixed it by putting a minus sign there. So if you have a charge that moves up and down in a wire, so it's changing back and forth, that's going to create electric fields that are going to be either going top to bottom or bottom to top, depending on what's going on at any moment. And magnetic fields that are either going around it clockwise or counterclockwise, depending on the direction of the charge moving. And so that's what creates an electromagnetic wave. So a typical antenna is a rod. Looking for, well, this will be my rod. Typical antenna is a rod. Here's longer. And you just have charge go up, down, up, down, up, down, and that makes oscillating electromagnetic waves. And then those electromagnetic waves, because of Maxwell's equations, will propagate. They'll keep going. Now, one thing that's unique here, because of this relationship, it turns out that you're not going to have electromagnetic waves going in all directions. If I have an electromagnetic wave going this direction, if that was the direction of the velocity, then the magnetic and electric fields would have to be perpendicular to that. But I can't make a magnetic field that's perpendicular to that on the axis. So I can't have any electromagnetic wave come out of the rod. So if you have a radio station, and the radio station, I don't know, when I grew up, my grandfather leased space in his pastures for radio antennas. So I was very familiar with those. If you had a radio antenna that was like this, and if it's pointing right at Aaron's not going to get that radio station because it can't send a wave that direction. But if I put it like this, then she's going to get it strongly. And if I put two antennae, one here and one here, then I'm going to have those two antennae are going to have their waves come out, and we can have constructive or destructive interference. And so we'll have locations like the center line between them. If I have them in phase, it's going to have a nice strong signal. Then we have other angles where we have a weak signal. And so we can get some directional ability. So in my grandfather's pasture, they actually had 3 antennae that they could use to construct where they want to broadcast and where they don't want to waste their energy. Now, how many people have a ham radio license? Just Brady? Okay. Brady and Carrie? I thought that everyone who was an engineering major had to have one. Well, so you guys, if you actually studied to learn and not to pass the test, will know that there's a lot that goes into antenna theory. There's lots of different variations and lots of things that go into it. It's not simple like I proclaim here in a general physics class. We proclaim the fundamentals, but if you want to make an effective antenna, it depends on what your specific wavelength or frequency is, what your goals are, what is the most efficient antenna. So here is what we call electric dipole antenna. This is what Heinrich Hertz used to test to make electromagnetic waves and see if they obeyed the same behaviors as light waves. So Heinrich Hertz, I think it was 1885-ish, somewhere in that ballpark, he did experiments and found that indeed these waves that Maxwell had predicted in 1873, so this was like a dozen years later, that they did obey the same rules as light waves. And so he said, okay, because they have the same rules, I'm going to accept that they're the same thing. And so that's what actually convinced people that he was right. So you just have an oscillating source here. And so if this side is positive and this side is negative, then current's going to flow the way the arrows are shown. And as the current reverses, the arrows are going to reverse. So you just have current going back and forth, creating electromagnetic waves. Now, if you're receiving, you have an antenna and you have a rod antenna. You guys may not even be old enough for when cell phones had antennae. But you used to have an antenna on your cell phone. You pull that out and you got a better signal. And if you had one today, you know what? You would get a better signal. But people didn't like them, and so they have tried to design antennae that fit within the case of the phone. Not as efficient, but not as annoying. So you have a rod. If that rod is aligned with the electric field, that electric field is going to cause electrons in the rod, since it's a conducting antenna. it's going to cause the electrons to have a force. The force is, of course, QE, right? Force due to electric field and charge. Electrons have a negative charge, so those electrons are going to go shooting downward in the picture on the left. That's going to make a current as the electrons go downward. And that current is what you measure and what you amplify for your radio signal. Now notice what's going to happen if you're not aligned. Will it still pick up the radio station? Yes, but not as efficiently. Because the force is going to be like that. That's the direction of the force on the electrons. And that's not parallel to it. It still has a component that's parallel to the antenna, so it's still going to cause a current, but it's not going to be as big. And so if you have your antenna oriented the right way, you'll get the strongest signal. So that's the standard antenna. If you have like an antenna on your car, you have a ground plane and the antenna sticking up from it, it's a half wave instead of a full wave, I think, antenna. So once again, different theories. This is another type of antenna. If you have an FM radio, you get the stereo, it usually has this little thing that looks like that you throw away. Well, what is this thing? It's got a bunch of wires like this. What is it? Okay, I heard some words, and I think I heard the word inductor. There are different names that are appropriate. An inductor is an appropriate name for it. I would say coil or solenoid more often. But a coil, a solenoid, inductor, they're all fundamentally the same thing. Just talking about it for different ways. It's a coil, or it's an inductor. If you align it so the magnetic field from your electromagnetic wave is going into and out of it, as the strength increases, it's going to make a current flowing one way. As it decreases, it's going to flow the other way. And so you'll create a current in here due to the change in flux. So this here is a flux antenna. It's measuring the magnetic flux and converting that magnetic flux information into a current signal. This one here was an electric field antenna. So electric field antenna versus magnetic flux antenna. But they'll both pick up the signal. And which one you use, it depends on your frequency and a few other details that I am not knowledgeable about on how you choose which one to use for your antenna. So we have these electromagnetic waves. Once it was agreed by everybody that light was an electromagnetic wave, then people set out to try to determine, so what do we have for the different types of electromagnetic waves? So up here we have what we call the electromagnetic spectrum. It's showing a range of frequencies from lowest frequency, which is radio waves, to highest frequency, which it shows as gamma rays here. So we have the spectrum. Low frequency means long wavelength. Remember from sound we talked about the relationship between frequency and wavelength. So we have our radio waves have long wavelengths and low frequencies. What's the frequency on an FM, or well, let's go with AM dial? Okay, like 800, 900. It goes all the way down to like 540 kilohertz. And then it goes up to somewhere 1,100 and some kilohertz. 1,600? Okay, 1,600 kilohertz. So our radio range for AM is in the ballpark of 1,000 kilohertz, which would be 1 megahertz. What about for FM? Goes from somewhere around 86 or so megahertz up to 106? And yeah, somewhere in that ballpark. So it's somewhere in the ballpark of 100 megahertz. So it's about 100 times the frequency of the AM. So those radio waves, we consider them low frequency. Megahertz low frequency. If I was singing in megahertz, that'd be really high frequency, right? So you have to adjust your frequency range for what's low and what's high between light and sound. Now, I brought up sound waves, singing. What kind of wave is a sound wave? We did cover this last semester, right? Sure we did. A sound wave is a longitudinal wave that's created by particles moving. So we have, like when I'm speaking here, I have air molecules that are having chain reactions moving the same direction as the sound waves go. An electromagnetic wave is a transverse wave because the velocity is perpendicular to both the electric field and the magnetic field. So it's transverse rather than longitudinal. And what is supporting it? It's not molecules moving and bouncing off of each other. It's electric and magnetic fields. Well, what do you have to have for electric or magnetic field to travel through space? Turns out the answer is nothing. But the early scientists didn't know that. The early scientists said, well, we have waves on water. They need to have a medium, water. We have sound waves. They need to have a medium, air, for instance. So they said there must be a medium for the electromagnetic waves. And so they started doing some research, trying to find this medium. And they gave it a name. They called it the ether, some ethereal thing that supports electromagnetic waves. And so try to find properties of this ether. So what kind of property would you try to find for this ether if you were an ancient scientist? By ancient, I mean somebody who lived at least 200 years ago.
The characteristic like the mass.
Okay, something about mass or density. Well, they couldn't find anything. One of the things that they really spent a lot of time was trying to find speed. Because you know that like if you have a sound wave, if you're moving the same direction as the air, then you're going to have the sound go a different speed than if you go in the opposite direction you. Right? If the air is stationary and you speed, it'll go the same speed in both directions. But if the air is blowing this way and I speed, it's going to go slower that direction because the medium itself is moving. And it's going to go faster that direction. So they tried to do experiments like this. So let's measure the speed of sound this direction versus this direction. And you know what they found? It was the same. No matter what they did, no matter how they varied things, they couldn't find a variation in the speed of sound. Now, people who believe in the flat earth say, that's because the earth isn't rotating. That's their interpretation. The physicist's interpretation is, we must have been wrong. There must not be an ether. That's the final conclusion that scientists have come to, that you do not need a medium for electromagnetic waves. They travel through a vacuum where there's nothing present. So continuing on with our spectrum, we have the relationship we've already learned that frequency multiplied by wavelength is equal to the speed. Now for light waves, we use C as the symbol for the speed of light. The speed of light is 299792458 meters per second exactly. That is defined as a constant, and the meter is a derived value. The meter is based on the speed of light. So we can take this and say, well, for a radio wave, for an AM radio wave, frequency is about 1 kilohertz. So that means wavelength is C over frequency, 2.998 times 10 to the 8 meters per second, divided by 10 to the third. I'll just put 1 over seconds for hertz. We see that that's going to have units of meters, and that would be about, okay, where did I make a mistake here? That doesn't make sense. Kilohertz though, right? Because I swear it comes out to be about a meter, and that's not about a meter. Or about a kilometer, still not a, that's roughly 3 times 10 to the 5 meters equals 300 kilometers. That's really long. I still can't, you can't make a mistake with this, can you? I mean, that's really easy math. Yes.
On the frequency chart there, it says AM radio next to 10 to the 6 hertz. So it'd be megahertz.
Oh, you're right. It is. It's 1,000 kilohertz. Whew. Thank you. That makes me feel a lot better. So that's about 300 meters. That's the ballpark I was looking for. So your AM radio, somewhere from a kilometer down to meters, that ballpark for its wavelengths. You go to the FM, it's shorter because you're 100, 1/100. So it's a meter shorter for FM. But those are still reasonable sized wavelengths. You keep moving up and you get to microwaves. What do we use microwaves for?
Food.
Okay, food. I use it for something else a lot more. I don't talk to anybody, but I use it for my internet communication here because your cell phone signals are using microwaves for communication. Infrared radiation, well, that's useful for things like night vision optics. You and I are giving off light that's in the infrared spectrum. And so if we make optics that detect infrared, we can view people in the dark. Then we have the visible spectrum. Notice how small the visible spectrum is compared to this entire thing. It's just a very small region. And then we get to ultraviolet. Now, technically, all of this is ultraviolet. Ultraviolet means above violet. Infrared, which I have to admit, when I was a child reading this in the encyclopedia, the World Book Encyclopedia, I pronounced it as infrared because that's what it looked like to me. And I didn't understand that infra means below, below red, above violet. So all of this in the box is above violet, ultraviolet. X-rays come from electrons in atomic or molecular cloud. Gamma rays come from nuclei. So the names X-rays and gamma rays is specific to the source. And typically, the gamma rays are highest frequency, highest energy. The X-rays are lower, and so that's why they're shown here. But you don't have clear segregations on those because it's based on the source, not on a wavelength range or a frequency range. So there's our electromagnetic spectrum. Notice that the visible spectrum goes from red at the longest wavelength to violet for the shortest wavelength. And so you have in between the whole Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. As far as I'm concerned, blue, indigo, violet, we can just combine those as one, but that's because I'm not very discerning. So with that said, how many people actually noticed what the range of wavelengths for visible light was? It's definitely 400 to 750. Okay, B and B. It logged you out in between.
Yeah.
That is annoying. You don't have much control over that. It doesn't have it yet.
Just downloading content, you can go.
Really?
Yeah.
Okay. That's perfect. Okay, so what we had was 15 people said 400 to 750. Have I told you that story or?
No.
When I was in graduate school, one of the guys I roomed with, and another physics graduate student, worked with a guy who was a genius. First thing he did when he came to graduate school was to ask his fellow classmates, do you know if we have a local society of Mensa? One day he was reading an article and it said, measured on that scale, and he went and asked my roommate, do you know if we have a nanometer scale? Nanometer. Roommate had to explain, no, that means it's tiny, measured on a tiny scale. not a physically tiny scale, but measurements. Anyway. So the correct answer here was 400 to 750 nanometers. If we look here, you can see 400 nanometers, 700 nanometers. I said 750. Why does that say 700? The fact is our eyes don't have a sharp cutoff you can't see here and you can't see there. It just becomes less and less sensitive. And 470, 750 give us a strategic advantage because if frequency or if wavelength is equal to 400 nanometers, then the frequency is equal to, rounding off, 3 times 10 to the 8th meters per second divided by 4 times 10 to the minus 7 meters. 3 divided by 4 we can all do in our heads, right? That's 7.5 times 10 to the, let's see, 7 and 7 is 14 hertz. Look, 400, 7.5. Obviously then, if the wavelength is equal to 750 nanometers, the frequency is equal to 4 times 10 to the 14th hertz. So the reason I always use 400 nanometers to 750 nanometers is because I have the numbers for the frequencies as well. Right? So I don't have to say, now was that frequency or was that wavelength? But of course, keep in mind, shortest wavelength, 400 nanometers, corresponds to the highest frequency, 7.5 times 10 to the 14th hertz. And so you see their numbers here, it's 4.3 instead of 4, and 700 instead of 750. Just a choice. I choose to make my life easier. So the visible spectrum. What color is the sun? Okay, white. Wow, how did you guys know it's white? Most people say yellow. Was it a question or something? Okay. Most people say it's yellow. The sun looks yellow in large part because of Rayleigh scattering. But if we take the temperature of the sun, has a surface temperature of about 6,000 kelvins, that color we interpret as white typically. In the visible range, sunlight has a spectrum that includes the visible as well as some infrared and some ultraviolet. But its peak is around green. It's green at the peak. Nobody says it's green because our eye has 3 kinds of cones. One that's most sensitive to green, one that's most sensitive to red, and one that's most sensitive to blue. And we interpret color by how much of each one of those is activated. And if they're activated about equally, we interpret that as white. And so while these are not exactly the same, they're going to activate them about equally, and it looks white to us. There is some variation between the spectrum the sun puts out and what we receive on Earth, because we have atmosphere between us and the sun. And so the atmosphere is absorbing light. So we have here the sun at the top of the atmosphere follows that yellow. So the sun at the top is roughly the black light's following the yellow, but it actually comes up a little higher there. And what we actually get is the red. And you see there's big parts missing. A lot of the ultraviolet is missing because the atmosphere absorbs it. It protects us from ultraviolet radiation. Specifically, the ozone absorbs ultraviolet radiation for us. If you have a hole in the ozone layer, you get more ultraviolet through. You get worse sunburns. It's more dangerous. We have absorption from our greenhouse gases. What's the primary greenhouse gas? Water, right? I circled water 4 different places. CO2 was just a minor thing here for the CO2. Why do we always talk about CO2 then? Yeah, that's the one that we can affect.